We're going to take a look at slant asymptotes today. So we heard this word a little while ago when we did horizontal asymptotes. We said that the power or the degree of the numerator versus the denominator determines where there is a horizontal asymptote or if it occurs. And we said that if the power of the numerator is greater than the power of the denominator, then there's no horizontal asymptote, but there could be a slant. So let's take a look at what it means to be a slant asymptote and when that would occur. Slant asymptotes, similar to vertical or horizontal, would be at some form of a line. So positive slope, it could be negative slope, and what that would look like would be something like this, where my graph maybe goes like this, has a regular vertical asymptote, and then over here it would like continue along a slanted line, kind of like that. So if the power of the numerator is greater than the power of the denominator by a value of 1, it must be 1 more degree on top than the degree on the bottom. Okay, this creates a break in our function that changes the function as the x value increases, the y value of the discontinuity would increase or decrease, meaning the asymptote is changing its position based on the y value. So as I move to the x value, this is up a little bit more. As I move to the next x value, it's up a little higher. As I move to the next x value, it's up a little higher. And it continually increases, in this case, at a ratio, at a slant, at a line. So we can say it's not at 3, x equals 3. It's not at y equals 0, but it's at 2x plus 1. The line 2x plus 1, for example. We find these by using division. So we had done synthetic division and long division. We must use that here if we have a slant asymptote. We divide the numerator by the denominator. We state where the asymptote occurs by the quotient, whatever the result is. Like I said, 2x plus 1, something like that. This will be an expression because the location of the discontinuity varies as the function x values increases. So a little confusing, but let's take a look at example 15. This is one built to show you a slant asymptote. We can take a look right away. First glance, the power of the numerator is 1 more than the power of the denominator. So this will have a slant asymptote, and we will do that in a second. This will not have a horizontal asymptote as per the rules that I had shown a little bit before. So first we're going to take a look at, just do the regular protocol we do at our normal rate. What is my domain? I look at the denominator. What is the 1x value? I cannot be. And that would be -2. I do that first before I cancel anything out. So I'm going to pause on range for a second. Discontinuities. Can I cancel? Well, let's factor the top. I'm going to do it slightly more quickly because just not to go too slow. Multiply to 20, add to 9. I got 4 and 5. And here is me factoring. So I have 2x plus 5, x plus 2, all over my x plus 2. I factored the top numerator, and I left with the denominator. I'm able to cancel that x plus 2. How nice. That means I have a removable discontinuity at x equals -2. Great. Is there a vertical asymptote? No, because I no longer have a denominator. My function reduces to just 2x plus 5. Do I have a horizontal asymptote? Also no, because the degree of the numerator is greater than the degree of the denominator. Do I have a slant asymptote? I'll write it up here. Yes, I do. Where would it be at? Well, it would be at the division between the two functions. I'm going to do this by the synthetic division way because we had done a little bit more synthetic division. I would divide using the -2, and I would do the coefficients to 2, 9, and 10. Here's my division. 2, -4, 5, and then I get over here a -10, and I get 0. Okay? No matter what, the remainder doesn't matter to us. So even if I got a remainder, it wouldn't matter. It doesn't affect it. Over here, I'm going to get a 2. The exponent reduces by 1. I get x plus 5. So here is where my slant asymptote occurs. For this example, interestingly enough, it is exactly at where my function reduces to. It happens to come out exactly there because I'm dividing by a factor. It'd be like dividing 32 by 2. It cancels out. It goes in evenly. I get a remainder of 0. If I divided this by x plus 1, there'd be a little bit more that occurs, and it would not come out to the same thing. So that's not always the case. But that is where my slant asymptote occurs. I like to keep it consistent with what we do down below. So I write at x equals 2x plus 5, meaning my graph looks like this. It's going to look like a line that goes like that, with a slight hole in my graph at -2. So even though this isn't really an asymptote we're used to, where I'm bending towards the value, like a vertical one, but never touching. Horizontal, I bend towards 0, for example, but I could cross it. For a slant asymptote, I am progressing along a value, but I'm like following that line completely. So there's no rules about not being able to cross or not. They get slightly less with those rules as we go down from vertical to horizontal to slant. Okay, y-intercept, I plug in 0. I'm going to plug it into my reduced form, and I get a 5. If I plugged it into the original, I would also get a 5. 10 over 2 is 5. I'm going to set it equal to 0 in order to get my x-intercept. -5 equals 2x. And I divide both sides by 2, and I get -5 over 2, comma 0. So all the procedures I did here are the same as we've done either on the homework or in class. The only additional one is this slant asymptote. And as we see here, it happens to follow this exact line. It's not always going to, but this is our first example. We'll do another one relatively quickly as well. My domain to start, I look at the bottom. I cannot be -1. Skip range for a second. Do I have anything I can cancel out? Not sure. Let's take a look. I'm going to factor this. -18 is what I'm looking to see what multiplies to that and adds to 3. I get 6 and 3, so plus 6x minus 3x minus 9. Take out a 2x. Take out a 3. 2x minus 3. And x plus 3 all over x plus 1. Here's an example. I cannot cancel anything out. I have no removable. The first one we've seen where I factored, and this is a totally different factor. Not a mistake. I can't factor everything out, so no removable. Is there a vertical asymptote? Yes. I have a factor on the bottom that remains, that -1, that x plus 1. So my -1 is where my vertical asymptote is. Horizontal asymptote is none because the degree of the numerator is greater than the degree of the denominator. Do I have a slant asymptote? Is the degree of the numerator 1 more than the degree of the denominator? Yes, it is. So I do have a slant asymptote. Let's find out where it is. I'm using my synthetic division divided by a -1, a 2, a 3, and a -9. Now, odds are I won't go in evenly to this. How do I know this factor, this binomial, won't go in evenly to this? Well, when I factored the top, there's not an x plus 1. So it'd be the same example if I were to factor out the number 20, and I try to divide that by 3. 3 is never a factor of 20, so it's not going to go in evenly. Same thing here. X plus 1 is not a factor of this trinomial. So I'm going to get a remainder that does not affect, I don't incorporate that into my slant asymptote. So let's take a look. I get -2, I get 1, I get -1, I get -10. I ignore that number. I don't include that number at all in my in my writing of the slant asymptote. It doesn't matter. That remainder does not matter. So my slant asymptote would be at 2x plus 1. It's going to look like my graph bends towards that 2x plus 1. Let's take a look at how this graphs. 2x squared plus 3x minus 9. 2x squared plus 3x minus 9 divided by x plus 1, I believe. X plus 1. And here we go. There's my graph. Right, and here's a pretty good example. If I zoom out, there we go. I have a slant asymptote at the line 2x plus 1. I'll make that dotted. And whoops. Here is my slant asymptote, and you can see it following exactly along that red line. So my graph is bending towards and bending away from that line 2x plus 1, slant asymptote. Okay, and I'll draw that picture here. It kind of went like that and like that. And the 2x plus 1 was right in the middle. Okay, and now we'll check our x and y intercepts. Again, if I for the y-intercept, I'm going to plug in 0. And I'm going to get a negative 9 over 1. So I get a negative 9, nice number. If I set it equal to 0, I'm going to get 2x minus 3, x plus 3 over x plus 1. They cancel. 2x minus 3 and x plus 3 equals 0. Right, because I'm running out of room here. 0 equals 2x minus 3 times x plus 3. And I would get my regular factoring 3 over 2 and negative 3. And if I take a look at my graph, here's my 3 over 2, and here's my negative 3, and here's my negative 9. So exactly as we wrote down there. You're going to have a couple of problems with practicing with slant asymptotes, just a new discontinuity in our list. We have listed 4. The only other one was jump, which occurs with piecewise functions. Okay, good luck on your work.